we're going to look at today with our kinematics is the difference between displacement, which we've been doing lots already, that's our formula S, and distance. Okay, so a really good example of difference between displacement and distance. You throw something up in the air and you catch it at the same place. Its displacement is 0. Right? This is one of the reasons that I actually don't like going for a run. Because I leave my front door of my house, I run, and I get back to the front door of my house a certain amount of time later. And mathematically, I think to myself, I could have got here a lot quicker if I hadn't have left. And then I could do something. And so it doesn't feel like, I know that it was probably good for me exercise-wise, and I should feel good about that. But the motivation isn't there. But sometimes if I need to get from point A to point B, and it used to be like, I used to live close to the school and it was walking distance. But if I needed to get home quicker, then I was like, now there's a purpose for running, and it made sense. Anyway, distance though is, it went up a meter, came down a meter, the ball has traveled 2 meters. That makes a difference. Can you imagine if our vehicles, you know how they have an odometer and say how much distance the car has traveled? If it was just a displacement odometer, it'd be like, if I bring it back to the dealership, it will say 0, and I'll be able to sell it for more money, because this car has never been driven. So that is the difference between displacement and distance. Now, when we do the integral, we get our displacement, because sometimes the area under the curve is above, and sometimes the area under the curve is below. And so throwing that ball up in the air with its velocity, with acceleration of gravity, part of its distance will be, or part of its displacement will be positive, and part of its displacement will be negative. And that will show up as the area under the curve, and will cancel each other out. If we want to find the distance, we need to find out when it's going in one direction, when it's going in the other direction. And the part that the area under the curve is negative, we have to make that positive. So one way of thinking about distance, if you were doing this algebraically without a calculator, you would split it up into those 2 sections, find each of those integrals on their own, and the negative one you would make positive by adding absolute value bars. If you were using technology right away from the beginning, I guess we're using x for distance, you could T1, T2, do the absolute value inside of the integral, because that would flip everything above the x-axis, making all of the areas under the curve positive to begin with, and that would get your distance. Okay? The problem with this, without a calculator, is we haven't done any rules for integrals of absolute values. So it's sort of like, ooh, right? What do you do with, what is the integral of the absolute value of x? Don't know, right? So we have to break it up if we're doing it by hand. If you're using technology, that makes the most sense. So these last 2 questions, they don't necessarily deal with distance per se. These last 2 questions are just, how do we use calculus to do our physics questions with very little information given? So here, a golf ball is thrown upwards with a velocity of 7 meters per second from the edge of a cliff 75 meters high how long will it take the golf ball to hit the ground? So it feels like we haven't been given enough information. It feels like we don't know where to start. Well, we start with maybe a nice diagram. Here's a cliff. Here's a little person throwing the ball up in the air. Oh, there was a little puddle here, and they hit it perfectly, and it made a splash. Okay? We're trying to figure out how long does it take for that golf ball to hit the ground. What do we know? We know a couple of pieces of information. We know that the cliff is 75 meters tall. So at time 0, the displacement is 75. We know an initial velocity. So at time 0, the velocity is 7 meters per second. The fact that that's positive means that ball is being thrown upwards. And of course, the only information we have from calculus and kinematics is phi.
Hey, Mr. Ross, sorry to interrupt you.
Hey. So I believe we were at phi, and we were trying to work, say, how can we use this? Well, we do know the other thing that we always know about real-life examples is acceleration due to gravity is negative 9.8. So we have now the ability to work backwards. And we can just use calculus to do that. So we say, oh, well, my velocity would be my integral of acceleration. And working backwards from that, I get a plus c. And since I know I have an initial velocity of 7, I find out that c is 7. So now I've got a velocity equation that's negative 9.8t plus 7. Next, I know that my displacement is my integral of velocity. So I can integrate the negative 9.8t plus 7 with respect to t, and I get add 1 to the exponent and divide. And I'll use the letter d here instead of c because we use c already. And since we know that the initial displacement is at 75, I can easily solve for d to be 75. And that gives our displacement formula to be negative 4.9 t squared plus 7t plus 75. So now we've got our equations for acceleration, because we knew it. We could work backwards to find velocity and work backwards to find displacement. And one of the things I mentioned before, and you can, on a test you'd have to show working backwards, but as a shortcut, the 75 there is always your initial displacement, okay? We talked about the 7 there being your initial velocity. And this value is always half of gravity as a result. So we could have maybe cheated and gone right to that equation and say, I know so much about calculus that I can do that, which is great, okay? But now you see where there wasn't a lot of information given. I didn't need to use any physics formulas. I could just develop my velocity formula, my displacement formula, just based on calculus. And now we can look back. What did the question actually ask us? How long did it take to hit the ground at the bottom of the cliff? Oh, I should have said puddle. Okay, so now we're trying to find time. We have to decipher Do I want to find time in a displacement, in a velocity formula? Which place am I trying to solve this? What could I use as right? This, we are trying to find time when, well, what does it mean when it hits the ground? When it hits the ground, its displacement will be at 0. So there's a little bit of analysis that has to happen. When the question is asked, we have to say, okay, I'm trying to find t. That part is easy. Everybody's like, when it says how long, okay, find t, no problem. But when it hits the ground, what does that mean? That means my displacement is 0. When it hits the ground, do I know what speed it's going, what its velocity is? No, not really. So I could figure that out as well. But at this point, I would go to my displacement equation, and I now need to set that equal to 0. Using your mathematical analysis skills, do you predict this will factor nicely? No. Good. I'm glad you look at that right away and go, yeah, that does not factor nicely at all. What should we do then? Well, if it was just a question that you had in your textbook and you were allowed technology, I'd probably go to Desmos or my graphing calculator, graph this, and find out where the x-intercept is. So that's basically when it's equal to 0, you're looking for an x-intercept. If this was a university question that they said no graphing calculators allowed, how do you solve a quadratic equation if you can't factor? You go to your quadratic formula. Either way, I've got the answer pre-figured out on a different slide here, so we don't have to waste time. There we go. Solving it, you would get 4.69 and negative 3.26. I hope you see that the negative 3.26 has to get x out, because it can't have happened 3 seconds before you throw it. That's what that means. Okay? But parabolas in real life always have 2 x-intercepts. Well, parabolas on a graph in real life. In real life, when you're throwing something, you only have part of that parabola, not all of it. So only the 4.69 seconds makes sense. What the other one is, if we go back to the diagram we drew, it would be like, oh, if this parabola went back in time, it would have come from the ground previously. You just were like, golf ball, come to me. And it would just have gone through the cliff, come back up to your hand, and then you could have just thrown it in the air. And so when we model something in real life, there are parts of it that don't make sense. What else is not going to make sense? Well, after that 4.69, that golf ball is not going to drill into the ground and keep going. Our life could be really different if we changed some rules around how things worked. It would be a little bit disastrous. Okay, so this question, I would say at the beginning, it seems like you're not given very much information, and you might feel a little bit lost. It's a kinematics question. You have to work your way backwards. The next one we're going to do is quite a bit harder. Part of what makes it harder is the units that were dealt with and the information that we're given. And the information that we're not given, but we can figure out. So, right, they've got fancy cars now that can do all sorts of things. My father-in-law just got a brand new electric car, and he let me drive it the other day. And it's so smart that I can be almost as dumb as possible when driving it. But I think you should still be careful, because if you decide to be dumb, it might not work once and then. But I put it on cruise control. I told it to look at the lines on the road. And then I sat there, and it turned around curves on Roblin. And when there was a car in front of me, so I had set my cruise at 75 kilometers per hour, just a little bit above speed level. I know. Your teacher, the respect is going down. But what happened was the car in front of me was going slower. So on my old cars, first of all, my old cars, I have to steer. And on my old cars, when you are going faster than the car in front of you, it is up to you to slow down. But on this car, it sensed the car in front of me. It automatically slowed down my cruise control to stay the same speed as the car in front of me. And if there was nobody oncoming traffic on the left lane, I could hit my signal light and the car would automatically pass without me doing anything. That's crazy. I don't have to do anything, right? And if I was on cruise control and that car decided to slow down to turn, I wouldn't even have to brake. It would automatically slow me down, and as soon as the car turned away, it would speed me back up to my cruise control. It's like, yeah, it's amazing. So, yeah, well, you can design these things that people don't have to say. Welcome to math class. Today, if you push this button on your desk, you will not have to think, and all your math problems will be solved for you. Congratulations, here's your diploma. And so I mean, there's good and bad. It's wonderful technology, okay? And to get there in that technology, there are so many people that have to do a lot of math to figure that out, but they're taking away that math from you in some ways. So this question's a little bit more difficult that way because of some of the things that we have. So we've designed a car that would increase its speed steadily until it reached 100 kilometers. That probably exists on my father-in-law's smart car. Just has to probably say, I want to go 100 kilometers, and then it just increases at its speed. And you might want to increase steadily, maybe it can figure out what's the best fuel efficiency or battery efficiency to do that. If it goes really fast at the beginning and uses more battery, then just slowly increases. They probably have mathematical equations figuring that out. So one day, Nathan goes on the highway and hits that button. He's starting at 0. So we know at time 0, his velocity is 0. And at time of 20 seconds, his velocity is at 100 kilometers per hour. How far did he go? Again, we start this question and we feel like we don't have a lot of information. Okay, so we still got this idea. And another thing that's going to cause us problems in this question is our units. 20 seconds, and our speed is in hours. So either we can decide to do everything in hours, but then 20 seconds is going to turn into a very, very small unit. We could change this to kilometers per second, but then the number in front is going to be very, very problematic. So the first thing that we're going to think about together is like, well, maybe our units, if we're using seconds here, in 20 seconds, I am guessing that he didn't travel many kilometers. I don't know if you've ever been in a car for 20 seconds. How far do you go? It's normally not like, oh, we reached Regina in 20 seconds, or something like that. So a better unit would be probably, if we want our units to be the same, we should convert this 100 kilometers per hour into meters per second. How do we do this? Okay? Some of you maybe even have like a formula in your head already to divide it. What is that formula? Divide by 3.6. So, some of you know, because you've had physics classes where you do this often enough, you divide by 3.6. What does that give us? 27 and 7/9 meters per second.
Hi,
Hello?
can I talk to you for one quick second?
All right. Now, if you don't know the 3.6, what do you have to do? Right? You have to convert. We start off with 100 kilometers per hour, right? As far as converting, some of the things that I find useful for converting, and this is true when you're converting anything, you can always take something and multiply it by 1. One of the things you can multiply here is, you know that 1 kilometer is 1,000 meters. And so this is multiplying by 1, but what it will do is it will cancel out my kilometers unit and change my units to meters. The next thing I could do is I could also multiply by 1 hour is how many seconds? Well, there's 60 minutes in an hour and 60 seconds in a minute. This would become 3,600 seconds. And then what happens here is my hour units cancel out. Okay? And the 1,000 over 3,600, if you simplify that, that becomes a 3.6 on the bottom, and your shortcut that you've memorized, now it's like, oh, if you forget that, you can figure it out. I always like things that if I need to remember, but I forget them, I can figure them out. And then I'm like, yay, I can free up my brain for something else. But then I can't forget it, for whatever reason. Right? So we figured it out on how to do it. There's a little lesson in conversions, because both of these things in the green box are basically multiplying by 1, but we're just changing the units. So you can do this with any conversion, right? You're traveling, and you know that 1 American dollar is $1.40 Canadian. And you're like, should I multiply? Should I divide? What should I do? Well, now you can just multiply by 1, and you'll know which to put on the top and which to put on the bottom by which units you want to cancel out. You can do any conversion easily this way. Okay, that still doesn't solve our problem. We just established our units. Now, what is somewhat problematic or hard in this question is we know there's an acceleration and that it's constant because it's accelerating at the same speed all the way from 0 up to 100 kilometers per hour. So we need to make it some variable. I'll just use k. K seems to be, I was going to use a new Greek letter on you guys, but we'll keep it simple. So our acceleration is k. We don't know what that is. But we know then that our velocity is the integral of k dt. In other words, our velocity will be kt plus c. And since we know our initial velocity is 0 when time is 0, you can solve that c has to be 0 as well. And so now we have a velocity formula that is just k times t. And since we know our second velocity at time is 20, that velocity is 27 and 7/9, I can plug the 27 and 7/9, and I can solve for k. I changed it back to a fraction, and I got k as 25/18. So now I know my velocity formula is 25/18t, and I can integrate that. Do we know its initial displacement? Yes. It hasn't moved at all. So when time is 0, the displacement is 0, which tells us that d will be 0. So our formula and the question initially was, how far has it traveled in those 20 seconds? $277.8 meters. So again, meters seems like a good unit. If we had kept things in kilometers, we would have got 0.2777 if we kept things in kilometers. So again, it's important to know what units you were using so you can write your final answer in those units as well. So in particular, what I found about this question that is hard understanding this line here that it says increases its speed steadily is telling you that its acceleration is staying a constant value. And then being willing to work with that even though you don't know that value. So we didn't know the acceleration. I put it as k, and at that point, normally or often as a student, we want to stop. Because, oh, I don't know something, so I can't keep going, right? That's very typical. And it's actually a good thing to do in a lot of situations, right? I don't know how to fly a helicopter. I shouldn't keep going. I should not just be like, well, let's see what this does. Okay, math is a little safer that way. You know, you might get a paper cut or get some lead on your fingertips, but you're not as dangerous as some other situations where if you don't know what you're doing, maybe you should stop. Sometimes in math, though, we don't know what our acceleration is, but we kept on going. We created our volume formula with that unknown. That then allowed us to solve for k. And once we had k, or once we had our acceleration, this question turned out to be very similar to the previous one. Previous one, it didn't tell you gravity, but you knew gravity. This one, it doesn't tell you it, but you know it's some number that's constant. And maybe if we work our way backwards, especially since they gave us so much information about velocity, we could figure that out. And with that, we are officially done integration.